Okay, so far in the course, we've looked at initial value problems. We have seen initial value problems. An example would be d square y dx square is f of x comma y. Given yx x0 is y0. And since this is a second order equation, you need two conditions. So dy dx at x equals 0 equals y0 prime. So these are initial values or initial conditions. A boundary value problem is a problem where at least one of these conditions are given at some value not at the initial value of x equals 0. So a boundary value problem has at least one condition not defined at x equals 0. So to take that same problem earlier, equals f of x y, we could be given y at x equals x0 equals y0. And we would maybe given x equals x1 at equals y1. So this second condition is a boundary value. It is not defined at x equals x0. Now you could also have it at dy by dx. So another example would be d square y dx square equals fx comma y, and you might be given dy by dx at x equals x1 equals y1 prime, and dy dx x equals x2 is y2 prime. So in this case, both these conditions are boundary values. They're not defined at x equals x0. Okay. Now, these problems, boundary value problems, are typically harder to solve. Or harder to solve than initial value problems. Okay, because you don't know how to start them from, right? You don't know what to initialize them. So you need some kind of a iterative way of figuring out the starting point so that after integrating over so many seconds or whatever the unit is, you end up with that value which is given to you. Okay, so we will look at two methods of solving boundary value problems. Boundary value problems. Okay, one is the shooting method. Yeah, I think I best illustrated this way. Let's say this is your integrator. example, Euler, RK4, whatever you want. Okay, all the integrators, in goes an initial value. Okay. So this is the value at x0. And out comes the values at different time intervals. So let's say that we know the value at x equals x1. This is y1. Yes, so here what happens is, let's say that we are given y at x equals x1 is y1 bar, okay? This is the boundary value, which is given. It's given. So if we supply this integrator with y0, out comes y1. So then we ask, okay, what if we supply with something which is slightly more than y0? What comes out? We look at the output and we sort of keep guessing what y0 would be so that y1 equals y1 bar. Okay, so example would be, let's say that this was given to be 2. We started with 1, but when we put in 1, so this is given. This is the value we desire. So we substitute some, we give some value, say 1, and out comes 1.8. Okay. Now 1.8 is different from 2. So we say, okay, maybe we should try 1.5. When you put 1.5, maybe what comes out is 2.5. Okay, then we say, okay, maybe the value is between 1 and 1.5. Maybe it's 1.2. So then when you put 1.2, maybe it's 2.1. So you just see, you can keep guessing an initial value till you see that the output is the desired value. So that is a shooting method, because you sort of put in an input, you shoot, in the sense you integrate over the whole horizon, look at the final value, check if it's the right value. If not, you change it. And so this typically involves some kind of a root finding. So this iteration, iterations are done using some root finding algorithm. And we've seen quite a few. Examples would be Newton-Raphson, bisection, so on. Okay, so that's one way. The second way is a shooting method. Sorry, finite difference method, my bad. Finite difference method. Okay, here what is done is you break up the ODE, or maybe I'll rewrite the ODE as a difference equation, right? Forward difference, backward difference, so on. Okay. Assume unknown at grid points. So example would be y0, y1, y2. Okay. Set up, so this is 1, this is 2. Set up conditions based on 1 and 2. That is, you have a difference equation, you have some unknowns. Just set up conditions. So you'll see that the conditions are for Eulers, it will be y 1 equals y0 plus delta times f of x comma y. That would be the condition. And then some point of time, the condition would be that you know the boundary value, it is whatever is given to you. And then solve for unknowns using free. Okay, so this will typically involve setting up conditions in free will lead to algebraic equations. Okay, so you could have a linear algebraic equation, ax equals b, or you may have a non-linear equation, f of equals 0. If it's linear equation, then you can use some of the methods we've learned, Gauss-Seidel, Jacobi method to solve for ax equals b. If it's a non-linear equation, then unfortunately you're stuck using a root finder again, solve for them. You've seen one example of a non-linear root finder for a multidimensional equations for, I think I gave it one of the homework questions. So in this case, linear equations, then use Gauss, Seidel, etc. If non-linear, you have to use a more fancier root finder, some similar to so they may get pretty complicated. So for purpose of the homework and class example and exam, which is taken by hand, I'll ensure that the problems you get, you can solve them by hand. You don't really have to use any complicated method, but maybe for the project, you might have a question where you might have to do this using code. So then you can pretty much it opens up to almost any problem because now you have access to a computer. Okay, so I'll show how these methods work with two examples, one for each. Okay, we'll solve the same problem using either methods, and we'll see that they'll obviously give the same answer, but we'll use different tools to do the problems because they are using different methods. Okay, so here is problem number 1. Okay. Okay, so let's start doing this. So first of all, what's the unknown? It's y x0 is equal to y0 is the unknown. Okay, what we know is our grid is 0.1, so the values are 0, 0.1, 0.2, 0.3, 0.4, 0.5, and we're given that y at x equals 0.5 is 1. Okay, so we also know that we need to use the Euler's method, which is yi plus 1 is yi plus delta x, f of xi, yi. So let's just sub that in, yi plus delta x. So this will be minus xi times yi. Okay, so I can maybe, just to make my life easy, just club things together. So I have 1 minus delta x xi. Let me write it like this, it's less confusing. Okay, so here's what we'll do. Xi, yi. So initial value 0. Initial yi is y0. This is the unknown, right? It's right here. We don't know anything about it. Okay. but we need to compute it. So yi plus 1, I'll use this formula now. So it says 1 minus, so let's do the calculation here. And the calculation answer I'll put back there, okay? So y1 equals 1 minus xi. So the initial value x0 is 0 times 0.1 times y0. So we see that y1 is y0. The first update is simply y0. Okay, so this calculation basically feeds here. Okay, next we have 0.1. This value should be written down here. Now we do the calculation for y2. It's 1 minus, I use this formula, xi is 0.1, delta x is 0.1 times y1. So that comes out to be 0.99 y1, right? But y1 is the same as y0. So this is 0.99 y0. So 0.99 y0. So this calculation is what feeds here. Okay, we just have to keep doing that till we reach 0.5. So 0.2, we start with 0.99 y0. Now let's do the calculation for y3. 1 minus xi will be 0.2. Delta x is 0.1. Y2 is y2 is 0.99 y0. So this is 1 minus 0.02, so 0.98 y2. But y2 is 0.99 y0. So this comes out to be 0.9702 y0. So 0.9702 y0. Goes here. Yes, so you just keep doing that. I will not do it. I would like you to do it yourself. So 0.9702 y0. Do the calculation here. It comes out to be 0.9411 y0. 0.9411 y0. Then when you do the same calculation, you get 0.9035 y0. Okay, so this is basically y at x equals 0.5, right? Using the 0.4 update to compute 0.5. But we know what yx 0.5 is. So this is 0.9035 is y of x equals 0.5, but that is given to us. It is 1. It is 1. So we can solve for, got to write y0, 9035 y0. So we can solve for y0 from this 1 divided by 0.9035. So that is equal to 1.107. So that is my answer. This is the answer. Yes, so see what you can see what I did. I just took y0, I integrated the equations, and then I ended up with the final value, the one which is given in terms of the initial value, and then solved for y0. So this is why this is harder, because you see what went through it. To get it, I basically had to compute y1 as a function of y0, y2 as a function of y0, y3 as a function of y0, y4 as a function of y0, y5 as a function of y0. So it just trickles in. Now the problem was so chosen that this condition, the condition is, highlight this. So this is our condition, right? This is the boundary value condition. boundary value condition. Okay, this condition is nice and linear, and so we could solve it by hand, but that need not be the case. If I had put something which was nonlinear to begin with, if this function was some nonlinear function, you would actually end up with a nonlinear value here. And clearly, if a nonlinear value exists, you cannot solve it by hand. Just go up to 0.4, not 0.5. We went to 0.5 actually. This is 0.4. So this is x of, this will make it clear. So this is x0, x1, x2, x3, x4. This is y0, y1, y2, y3, y4. This column is I plus 1, so it's y5, sorry, y1, y2, y3, y4, and y5. So this is y5. So we went up to y5. So you don't have to go another step. Okay. Okay, so you can expect something like this. It should be solvable by hand. Okay, now this was one method. The second method we'll talk about is the finite difference method. So I'll show you how this is different from this one. And you can choose which one you would use. Yeah.
So A0 or the answer that we got for like 0.99 Y0.
Why do I do this?
Yeah,
Sure, yeah. So this is 0.9 Y2, 98 Y2, but Y2 is 0.99 Y0. So this 0.92 sits here. This Y2 is 0.99 Y0, which is substituted here. Did I delete something here? This was Y2. I want everything in terms of Y0. Any other question? Okay, so let's do the same problem using finite difference. Okay. So let's see how to do this. So first of all, oh, I forgot to put the grid size. And grid size delta x is 0.1. Let's use the same one. So xi is 0, 0.1, 0.2, 0.3, 0.4, 0.5. What we need to do here is we need to create variables for yi, the unknown. Those will be the unknowns. So we have y0, y1, y2, y3, y4, and y5, right? There are 5 unknowns for those 5 grid points. Now, what is asked is to us is we are asked to compute y0. We don't know what y0 is, right? This one is the unknown. But y5 is known. It's basically 1. It's this condition here. So we need to set up equations which relate y5 with y0, and in fact, all the other variables. So for that, we'll use the Euler's method, which states that yi plus 1 is yi plus delta x f of xi yi. So we can do some math here. yi plus delta x. In this particular case, f of xy is minus xi yi. So this is 1 minus xi delta x yi. Okay, so let's now proceed to compute the equations for relating the different y's, which are now our unknowns. Okay, so I equals 0. I just put I equals 0 in this formula. So y1 equals 1 minus x0. So x0 is 0. Delta x is 0.1. Y0 is y0. So we get, so this whole thing comes out to be y0. Set it down, y0. So the first equation I have is y1 minus y0 is 0. If we put I equals 1, we have y2 equals 1 minus xi is 0.1, delta x is 0.1, y0, well, next one is I equals 1, so y1. This comes out to be 1 minus 0.01, so 0.99 y1. So my next equation is y2 minus 0.99 y1 equals 0. Put I equals 3, sorry, I equals 2. Y3 equals 1 minus xi, I is 0.2. Delta x is 0.1. Yi would be y2. This comes out to be 1 minus 0.02, so 0.98 y2. So my third equation is y3 minus 0.98 y2 equals 0. Okay, keep doing that. Y4 equals 1 minus 0.3 times 0.1. This will be 0.97 y3. So y4 minus 0.97 y3 0. And then there's clearly a pattern. Y is 1 minus 0.4 times 0.1 y4 0.96 y4. And so y5 minus 0.96 y4 equals 0. Okay, so I'm going to use these to set up an equation, okay, which I'll write down here. So there are how many unknowns? Well, we have y0, y1, y2, y3, y4, but y5 is known, right? y5 is equal to 1. It's given here. This is 1. It's also given here. So y5 is not an unknown. So we'll have to set 5 equations for the 5, but only y0 to all the way to 4 would be unknowns. So the first one will be an equation like this: y0, y1, y2, y3, y4. So the first equation will be the minus 1 for y0, plus 1 for y1, and there'll be 3 more zeros. Next, there's a 0 for y0, minus 0.999 for y1, 1 for y2, 0, 0, 0, 0, 0.98, negative 0.98 for y2, 1, 0, then 0, 0, 0, minus 0.97, 1. So it's this equation. Okay, and then we have 0, 0, 0, 0. There's a 0.96 for y4. Right hand side, we have 0, 0, 0, 0, except for the last equation, which I need to move to this side. So it'll be negative 1. Okay, now all I need to do is I need to do A/B in Octave or MATLAB, and that will give me all the constants, the unknowns. So solving, get y0 is 1.1069, y1 is 1.1069, y2 is 1.0958, y3 is 1.0739, y4 is 1.0417. All those values actually don't really matter. What matters is this one. This is the one we were after. So that's the answer, 1.1061, the first value. Yeah, question. Why is the last number -1? Yes, good question. So this is Wi-Fi is 1, but the way I wrote this equation is that I need to move this 1 on the other side. So when I move it on the other side, it becomes -1. Yeah, so the answer here is 1.1069. If you look at the solution we obtained earlier, actually rounded it up. It's 1.107 I got. It's off by 0.0001. 1069 versus 1.107, right? Very close. So we got 1.1069 from the next page. So it's off by 1e -4, right? So it's